Okay, we are very happy to have today Jérôme Renault from the Toulouse School of Economics. Jérôme is an expert in dynamic games, in optimization control, and recently he started being interested in artificial intelligence in games. He's one of the authors of the textbook Mathematical Foundations of Game Theory with Rida Laraki and Sylvain Saurin, and also of a book in French, right? The Théorie de Jeux, Introduction à la théorie de jeux répétés, with Rida Laraki and Tristan Tomala. So, and of dozens and dozens and dozens of great research articles. And today we'll have Jérôme teach us. So, Jérôme, the stage is yours.
Thank you, Alan. Thank you very much. I think it's my second invitation here, so thank you. And today I will present a joint work with Etienne de Montbrun, who is a PhD student here in Toulouse. He may be connected, I'm not sure. I think so, he should. And so we are both part of Toulouse School of Economics, but also of Amity, which is an AI institute in Toulouse. And the fellowship of Etienne comes from Amity, and it's part of my game theory chair on game theory on artificial intelligence. So the field is a bit new to me, and it's the first time I'm presenting the paper. So please, if you have any feedback, we have many references already, but please interrupt me, and if you have any thought, I would be interested in them. Okay, so let's start. So you all know what is a gradient descent. So imagine you want to minimize a function g, which is nice, maybe convex with a Lipschitz gradient. You fix a step size eta, and you do a gradient descent. You want to approach the minimum of the function. Okay, suppose now you're in the particular case when you want to minimize a function, you want to find y, which minimizes a function defined like this with a supremum. Okay. So there are many possibilities. You can either treat this function as one function of y, or you can do many things. And one of them is, I don't know if we can really call this the game theoretic approach, or at least it's one game theoretic approach. You can consider the zero-sum game associated to the g function. Okay, so as usual, player one chooses an action in x, player two in y, and player one wants to maximize g of x. Okay, assuming the g function is nice on the game, we have this equality here, which means that the game has a value and both players, they have optimal strategies. So there is an equilibrium or saddle point. Then it's natural to look at the gradient descent ascent. Okay, so given a step size eta, you look at this algorithm. Okay, here there is a plus because player one is maximizing and a minus because player two is minimizing. If it converges to a point, it's easy to see that it has to be an equilibrium or a saddle point of the game, and then the limit of the yt is achieving the minimum here. So this is one way to try to solve this problem of finding y, minimizing this function, the game theoretic approach by using a zero-sum game. There are many other ways. So this is used in many contexts. One of them, which is let's say very popular, used a lot. For instance, is the case of GANs, Generative Adversarial Networks. So I don't know if you all know about GANs, so I can tell a few descriptions and then come back to the optimization. The goal of GANs is to simulate a distribution from high-dimensional data. You know you have a lot of pictures of cats, and you want to create a new cat which looks like a cat but which doesn't exist. You want to simulate a law that you imperfectly know. You don't want to compute the law. You want to simulate, to generate elements which look like coming from this law. So in the original variant was introduced like almost 8 or 9 years ago by a good fellow. And for instance, this is like a joke. It's a painting, as old painting called Bellamy, a joke with Goodfellow in French. And the signature here that maybe you cannot see is this zero-sum game formula. Okay, so I will explain where it comes from. So here also, these are pictures of people who don't exist. So it's very realistic, and it's quite impossible to see. It's impossible, I think, for humans to see if these people exist or not, if you don't know it. So where does this formula come from? It comes from a game. That's something we can see as a zero-sum game between two players. So one player is a generator. He is minimizing. On the discriminator, he is maximizing. What is doing the generator? He is given some noise, Z, maybe typically some Gaussian noise in dimension maybe 100. And then he is building a function capital G. Given this noise, he has to construct a fake image, which should look like a cat or like a human being, like let's say the face of someone. And what happened is that the discriminator is shown one image, maybe this image. But with probability 1/2, it's a real image, or with probability 1/2, it's a fake image. And the goal of the discriminator is to give some number, d of x, which is between 0 and 1. And if it's 1, if he is sure that it's a true image, and if it's 0, if he's sure it's a fake image. And 50%, 70%, you imagine what it means. Okay, so here we can write this as a game, or we can view this problem as a game. So the generator minimizes, the discriminator maximizes, and this is a payoff function. What does it represent? If x follows the truth, then d should be close to 1. Okay, you want to maximize this log. If the image follows not the truth, but what is generated by the generator, you want d to be close to 0, so you want to maximize this. You can see this as a game. What we are interested in is this function, g here. And in practice, you cannot take any function. They are both, usually, these functions are given by neural networks, deep neural networks. So this theta j is a parameter for the generator, and theta d is a parameter of the discriminator. So usually, you have several thousands. It's in dimension several thousands, maybe 10,000, maybe millions. Okay, so it's really in high dimension, but it is a zero-sum game, and you want to compute this game. Okay, so the same formula again. This is what the discriminator tries to do. This is what the generator tries to do. If there was no parameters here, you could choose any law, and if you could emulate exactly the true law, this is what would be optimal for the generator, but sometimes it is not available, and especially you cannot use any function you like. On training GANs, which means that are looking for this optimal theta g here, typically what do? They alternate between gradient descent ascent, gradient ascent for the discriminator, which maximizes, and gradient descent on the generator, which minimizes. Stochastic in most of the case with mini batch, and there are many variants. Sometimes it's not 1-1, it's not 1-1, it's do one step for the generator and then many steps for the discriminator. And you have a lot of things, and they modify a bit the function. It's not really zero-sum to get rid of the slopes, infinite slopes, things like this. So it's mini cooking. It works very well in practice. Sometimes too well. You probably have heard about the deep fakes. You can make a video with your picture and make you do crazy things. Nobody will see the difference. But we don't. The convergence is not well understood theoretically, and this work is, let's say, in the spirit of trying to prove convergence for this kind of algorithm. Okay, so let's come back to our problem. Problem is to find y which minimizes this supremum. Here we make a very strong assumption. We say, okay, let's assume the g function is very simple. It's bilinear. Okay, so these are like the simplest function which makes sense in the strategic context. If you have one variable, you will try first with linear maps. So here we do with bilinear maps. So it was introduced in a seminal paper a few years ago, 5 years ago, and many papers study this case. Okay, and the first case. So here we have some algorithm. We want to try to see where it works, and we look at the simplest case where it makes sense. Okay. So it is well known that the basic gradient descent ascent does not always converge. Okay, even in a simple case, which is called matching pennies, but be careful. Huh? Here it is unconstrained. So we don't play in the same place. We can have any vectors in Rn for player 1 and any vector in Rp for player 2. So even in this case, you can see that the algorithm doesn't converge, it goes to infinity. So what is done to prove convergence? There are many ways to do, like proximal point method, particular case, extra gradient, things which are similar. Here, we'll concentrate only on this case, which is called optimistic gradient descent ascent. We add this blue term here. Okay, this blue term, and for the matrix case, for the bilinear case, and this is just this formula. Okay, this formula again. So back to the simplest case, where g of xy is just x times y. So imagine the game where player 1 chooses x, player 2 chooses y, and the payoff for player 1 is xy, zero-sum game. If you do gradient descent, you can, so without the blue term, you can write this as a linear system, dynamical linear system. And here zt is simply xt yt. In this case, zt is a vector xt yt. And you see from this formula that it is given by this matrix lambda. This one is this one, this 2 eta is this 2 eta. The determinant of this matrix is higher than 1. So one eigenvalue will be with modulus strictly more than 1, which will induce that some part will go to infinity. So if we start here, here the equilibrium is just 0, 0. It's very simple. If we start here, it will go like this and go to infinity. On the contrary, if we use the optimistic gradient descent ascent, so we add these blue terms, still we have a linear dynamical system. So now zt is, it has 4 coordinates, because we come back to stage t minus 1. So now zt will be the vector like xt, yt, xt minus 1, yt minus 1. You can write it as a linear dynamical system with this matrix. Okay, and you can see very easily that if eta is small enough, here we'll only consider fixed step size. They do not decrease with time. If eta is small enough, the spectral radius of the matrix is strictly less than 1. So by Gelfand theorem, this matrix goes to 0, which implies that zt goes to 0. We reach a saddle point. Okay. So this is the end of the introduction. What do we do here in this paper? So we first clarify and extend previous results. In this case of optimistic gradient descent ascent for a bilinear game, for zero-sum bilinear games. Okay, so we'll prove stuff. Some are already known, some are new. So exponential or linear convergence to a saddle point. We'll have a precise experiment of the convergence rate. We'll study exactly the range of step size eta where we have convergence, and this will allow us to find the optimal step size. This is part 1. Part 2, we will generalize the algorithm to general sum games. Okay, now we'll have player 1, player 2, both player functional bilinear, but now it's a general sum games. And we'll give sufficient condition for convergence to a Nash equilibrium. Or in some case, in a more general case, we will have sufficient condition for either convergence to a Nash equilibrium or convergence of both payoff to plus infinity, which is also interesting. If payoff of each player goes to plus infinity, okay, it's not a Nash equilibrium, but still maybe it's a good outcome. And in the last part, we'll come back to our problem, find y, which minimizes this supremum. Okay, and we will use we will not stick to the zero-sum game. We'll define some artificial general sum game, non-zero sum, that will converge to the saddle point, the same saddle point as in one, but in a much faster way, using this result here, existence under some conditions of convergence in general sum bilinear games. It will improve a lot the rate of convergence of a min-max problem, of a zero-sum problem, by looking at general sum, non-zero sum problems. And then we will illustrate on a very simple example of GAN, but another kind of assertion GAN if we have time. Okay, so for this presentation, let's forget about the linear terms here. So we just take g of xy is x transpose ay. So x is a column vector, y is a column vector, and A is a matrix. So here's a set of equilibria or saddle points of the zero-sum game is the kernel of A transpose for player 1 and the kernel of A for player 2. So in particular, 0, 0 is a saddle point. So this is a bit unusual here. We have a problem. We know already that 0, 0 is a saddle point. So the problem is trivial. But what we want to do is to see when our algorithm performs well, and we start with simple bilinear payoff functions. Okay, if I need to see what is a saddle point, I can say already 0, 0. But two things. First, we have linear terms that I don't include in the presentation to avoid notations. And also, this is not the goal. The goal is to see when the optimistic gradient descent ascent performs well. So I think it's a good stop here if you have questions. This was the introduction, and we go to part 1 on zero-sum games. If not, I continue. So, theorem. This theorem will last for 2 slides, but the most important slide is the first one. So start with any matrix A, which can be rectangular, and a positive step size eta. So define mu max, which is the highest eigenvalue of A times A transpose. And this is a spectrum, set of eigenvalues, complex eigenvalues, but here it's a symmetric matrix, A transpose yeah. So if you want, it is a square of the highest singular value of. And mu min is the smallest positive eigenvalue of A transpose. Okay. So what do we know? What do we prove? If eta is high, if the set size is too high, if eta square, 3 eta square is mu max is higher than 1, then for some initial point, we will not have convergence. Okay. So in the second, we assume eta is smaller than this threshold, which depends on the matrix A, of course. We fix the initialization. And then we have many results. So first, you can prove that xtyt under the optimistic gradient descent ascent converges to a Nash equilibrium or to saddle point. And which one? So the limit for x infinity, it is the orthogonal projection of x0 onto the set of optimal strategy of player 1. And y affini is the orthogonal projection of y0 onto the set of optimal strategy of player 2. So what is a bit surprising when you learn about this algorithm is that this limit only depends on x0. It doesn't depend on eta, and it doesn't depend on y0, x minus 1, y minus 1. Okay, and the same for y infinity. Okay. Now, eta is less than 1 over square root of 3 mu max, so it can be either less than 1/2 of square root of mu max or between this one and this one. If eta is small, the convergence is exponential. So in this literature, they say linear. They say linear, and this is called the convergence rate. And we have a precise estimate on the speed. This is true for everything. It's important in applications. So the rate, the convergence rate, lambda eta, which is something strictly less than 1, this is strictly less than 1, is exactly this. And it is the optimal rate You cannot find something smaller where this inequality would be true. It's given square root of 1/2 of 1 plus. This constant C, we had a hard time, but we could write it in this way. And D is just the distance between the initialization, let's say, and the equilibrium point. Okay, so this is what we have. The next slide, I have the case where eta is between this number and this number. It is similar but more complex. What is the difference? Is that, okay, we'll have several cases depending on if the spectrum of A transpose A contains a particular point.
May I ask a short clarification question?
Sure,
please?
sure.
So these cases are all completely non-intersecting, are they or no?
2 and 3, yeah, they don't intersect.
They
Okay.
never. So basically, you exhaust all the space with those. Basically, it's a partition of the space of the possibilities, right?
Exactly. The only case we don't do is eta equal to this number. Okay.
Okay.
It is doable, but I'm not sure it's very interesting. It is doable.
Could you please also repeat case 1, please, if you have time, if possible?
1, so it's not case 1. Case 1, it is true. So we have 3 properties. Eta is smaller than this. Then 1, 2, and 3 are true. So then we have xt, yt from the optimistic gradient descent ascent will converge, will have a limit. Okay, and we characterize the limit.
Oh, thank you.
And then we say something about
Jérôme, can you also say something about the kernel? You said these are the set of optimal strategies, but doesn't that suppose full support? Couldn't you have some things, if you restrict it to the support which is not in the kernel and just has worse payoff?
I'm not sure I understand.
So when you say kernel of AT, that means all these other things that vector that sum this thing to 0, meaning you guarantee payoff 0, because that is the value of the game, correct? That's why you look at the kernel
of AT is just a set of x such that ATX is 0.
Yes. So my question is, do you really have to make everything 0, every column? Because or row, I mean, whatever you look at, because
yes, if you look at this zero-sum game, okay, x is in Rn, y is in Rp. Remember, we're not in the simplex here. We look at the unconstrained games. So this is exactly the set of equilibrium.
Oh, I see. That's what you said there. Okay, thank you. So you really have to have everything is in a sense possibly a plate and therefore needs to be set to 0. Okay, good.
This is
no inequalities. That's what I understand here. Yeah, thank you.
Yeah, no inequalities.
Perfect. Thanks.
Okay, so the third case, okay, don't read this, I think, but we can handle it. It's more technical, but we can do it also. So what is the proof? The proof is what you think. Nothing really unusual. It's just you do spectral analysis for the matrix capital lambda. You have a linear dynamical system. To get the C here, you need to struggle a bit to look at the angles between the different eigenspaces. And to look at this case 3, it's a bit, you need to look at the case where 1, the real 1 is one of the eigenvalue of the linear dynamical system, and then you need to look at the normal of the Jordan normal form, but which was not done before, but it is doable. Okay, and here we compare with previous result of the literature. So as I told you, some results were known, but we also provide new results and we clarify, I think, all the cases here. Okay. So as a corollary, now we know that for every eta small enough, we know the convergence is exponential. Call it exponential or linear as you like. we can try to find eta, which minimizes the rate of convergence lambda eta. This is very natural. So what will play an important role here is this number alpha, which is a ratio between the smallest positive eigenvalue of A transpose A and the highest one. So it's a number between 0 and 1. Cannot be 0, it's between 0 and 1. It's linked to the condition number of the matrix A in numerical analysis. Beta is just something which is increasing with alpha. It's a way to write things. And here are the optimal values. So the best is to choose eta star, satisfying this. And it is also always, it's quite interesting to notice, I think, it's always the case that the interesting eta belongs to this slide, not the first one, okay? So this is why we needed to tackle these cases, okay? It's always the case that we are in this case to be optimal, and this is exactly the optimal rate of convergence you can get when you do optimistic gradient descent ascent on this game. Okay, you define alpha, then beta is just some kind of alpha, and we have this. So it's always at least square root of 2 divided by 2. You cannot go lower, never. And it goes up to 1. When is it better? It's better when beta or when alpha is large, which means that this is large if it's close to 1. So it's large when A transpose A has a unique positive eigenvalue. So for instance, if A is one homothéty, or when A is an orthogonal matrix, we are in good shape for doing for the speed of convergence. Is it fine for this? So this is a contribution to the zero-sum games. And now I'm going to the general sum game. Okay. So first, we just extend the definition to a general sum game, and this is exactly what you think. No surprise. Now we have two matrices, A and B. Player 1 wants to maximize this. Player 2 wants to maximize this. And we do optimistic gradient descent ascent with these formulas. Now you compute. What is the set of Nash equilibria of this game? It's very simple. It's this set. So kernel of B transpose times kernel of A. It is easy to see that if the algorithm converges, the limit can only be a Nash equilibrium. Okay, as before, it can be written as a linear dynamical system. And now this is the capital lambda matrix. And we can study, we can do spectral analysis about this matrix. We can study the eigenvalues, the eigenspaces, etc. So it's not too difficult to look at the spectrum of the matrix lambda because of the following results. So we define for every complex number mu the set S star of mu, which is a set of complex numbers lambda satisfying this polynomial equation. So it's a very simple polynomial equation of degree 4, but you can have two equations of degree 2. And the spectrum of lambda is just the union for all mu eigenvalue of B transpose A or A B transpose of S star of mu. Okay, so now we just need to compute this for every mu and to say what happens if about the modulus of these eigenvalues. And if we have an eigenvalue which is 1, we need to look at the dimension of the eigenspace, of dimension of the characteristic space, are they equal, to see if the iterate of capital lambda converge or not. Okay. So what do we see here? We see that convergence may fail in the simplest case. So this game is a bit simple. Player 1 chooses X, a real number. Player 2 chooses Y, a real number. And they both have payoff X times Y. So what is the set of equilibria of this game? It's just 0, 0. It's a unique Nash equilibrium. But what we can see here is that in many cases, depending on the initialization, but in most cases, xt and yt goes to plus infinity. So we cannot hope convergence to a Nash equilibrium. Okay, so let's look at sufficient conditions for convergence. Okay. So this is the second theorem. So we are in the general sum case, sufficient convergence conditions for convergence. So takes two matrices, A and B, and assume the spectrum of B transpose A is a subset of the real line, but of the non-positive real line. Okay. Let eta be small enough. So here we just have this case. We won't go to 1 over square root of 3 mu max. We will not need it, so we don't look at it. We don't characterize here all the step size where we have convergence. So what is mu max here? Mu max is, and we extend the definition of the zero-sum case, the largest eigenvalue of minus B transpose A. And let's assume, in addition to assuming this, let's assume that either we have hypothesis H1 or H2. Okay. So H1 is A and B or square invertible, and H2 is B transpose A is diagonalizable, and we have this condition on the kernel and the images of the matrices. If we are in this case, now which is specific, then what do we have? For every initialization, the algorithm converges to a Nash equilibrium. We can characterize the limit as before. So x infinity will be the projection of x0 onto the set of the Nash equilibrium component for player 1, the kernel of B transpose, and along this vector space, image the range of A. This is the range of A. And y infinity is the projection of y0 onto the kernel of A along this subset, the range of B transpose. And the convergence is exponential. And what is the rate? The rate is given by this number. Okay, very similar to before, when now mu min is the smallest positive eigenvalue of, let's say, the smallest positive mu, such that minus mu is in the spectrum of B transpose A. So the smallest positive eigenvalue of minus B transpose A. This is what we have. Remark, look at eta. So eta cannot be higher in this theorem than this number. If we want to minimize lambda eta, we take eta large enough, because this is decreasing in eta. So we take eta square is 1 over 4 of mu max. So we know that lambda eta will be for sure greater than this number. But we can make it very close to this number. If we take eta close to the maximal bound, then lambda eta will be close to this one. So this gave us an idea of the optimal rate of convergence given by this theorem. We don't know if it's the optimal one for this setup, but this is not really what we're interested in. We also have a counterexample where this assumption is satisfied. Okay, this assumption is satisfied. We don't have this. So all these assumptions are somehow necessary. Okay. So this is sufficient convergence condition for the convergence in the general sum case. Now remember the case where A is equal to B is 1. The payoff function for each player is x times y. The unique Nash is 0, 0. But if I have to play this game, if both players pay 1 million, it's more interesting. They both have a very good payoff. So in some case, wow. In some case, having payoff going to plus infinity is also interesting, and this is what we care in the third theorem. So we have two matrices. Assume this, that the spectrum of B transpose A is including the real line, but it can also have positive points or negative points. And we assume H2. Then we can prove that either we converge to a Nash equilibrium or the payoffs of both players converge to plus infinity, which is, in our view, it can be considered as some generalized Nash equilibrium. This dynamics where the payoff of both players goes to plus infinity. It is maybe the best that we can hope. So this is the interest of this theorem. This assumption here, or in particular true if B is equal to A, for instance. In common payoff games, suppose A is equal to B. So both players have the same payoff. This theorem says that either we converge to Nash equilibrium, or both payoffs goes to plus infinity. Also, we recover the case of zero-sum game. It's also true in the case where A and B, they are square matrices, and then B transpose A diagonalizable with n distinct non-zero real eigenvalues. And we have a counterexample where we have H2 is true, but we have eigenvalues which are complex and non-null. So this is our theorem about somehow coordination or a cooperation induced by the algorithm in the case of in some case of general sum games. Okay, so this is the end of part 2 about general sum games, and now we can come back to the original problem on using this result. Do you have some questions at this point? If no, I continue. So let's come back to our problem. So for the presentation, as I told you, we assume B is 0. So we don't have this part, we don't have this part. Otherwise, remember, we need, for the approach to make sense, I mean to work, to assume that the saddle point exists. So we need these conditions. So we want to find y achieving the minimum here. What can we do? We can use the first theorem, option 1. Run optimistic gradient descent ascent for the zero-sum game with the payoff x transpose ay with some step size eta, which is has to be smaller than this bound. We know this perfectly by theorem. So yt will converge to the original projection of y0 on the kernel of A, and this was we have this. The convergence rate is lambda eta, which is a maximum of two numbers, this one or this one. Okay. If I want to go back to theorem 1, maybe I understand now better a question, and I'm not sure I replied accordingly. This case here, okay, it is disjoint from this case. But the rate here we have is a generalization of lambda eta. So this formula is true for every eta, even smaller than this parameter. So this is a general formula for the rate. Here. Okay, so this we can use theorem 1. But we can now optimize in eta. We have done this exercise. So option 1 bis, option 1 improve is optimize the step size eta. We take the optimal one. This was the formula I gave you before. We find this lambda star that we have seen before, and this is the best we can do. So remember, this is better when alpha is large. So it is better when A transpose A has a unique non-zero, unique positive eigenvalue. Okay. Option 2. Remember theorem 2. In theorem 2, it was about general sum games. We gave many sufficient conditions, but which imply we have convergence to a Nash equilibrium, and with some rate, some rate lambda eta. And this rate was always at least this number, and sometimes it was very close. If we choose eta up to the close to the upper bound. Where what are mu min and mu max? Let me recall. Mu min is the smallest positive mu, so that minus mu is in the spectrum of B transpose A, and mu max is the highest eigenvalue of minus B transpose A. And we had some assumption in theorem 2, including this one. So when is mu min close to mu max? So it's better, convergence is faster if B transpose A has a single non-zero eigenvalue, which is negative. So for instance, if B transpose is like minus the inverse of A, it is very nice because we have the identity matrix, we have minus the identity matrix, which unique eigenvalue is -1. Okay, so let's generalize this. So here A is any matrix, it's not square, it's not invertible. So let's use the generalized inverse, Moore-Penrose inverse A plus of A, and define B like this. Okay, we have a problem, a zero-sum problem with just one matrix A. We define B with this formula. So for instance, if A is this matrix, this is a generalized inverse, and this is B minus the transpose of A plus. We can check now, with this B, or the assumption of theorem 2 satisfied. We had many assumptions. And it turns out that the assumption of theorem 2 are always satisfied. Starting from any matrix A, if you define B like this, the couple AB will satisfy the assumption of theorem 2, which was this one. So we can apply theorem 2 to the general sum game, this game, and we will get convergence of YT and XT to the same limit. You can check it will give exactly the same limit as if you use theorem 1, but the rate will be faster because now we will be in the good case where this is exactly 1. So these terms cancel, and we obtain the rate of square root 1 over square root of 2. And this is probably, or maybe the main idea here. So this is summarized in theorem 4. So consider any matrix A and take eta, which can be even equal to 1/2. We don't need to care now to know what is eta compared to some eigenvalue. You take 1/2 if you want. Run optimistic gradient descent ascent for these payoffs, where B is some matrix you have defined, which is minus the transpose of A plus. Okay. Then you have converged exactly to the same element as in theorem 1. Moreover, the convergence is exponential, and this is exactly the rate. If eta is strictly less than 1/2. And if eta is equal to 1/2, you have 1 over square root of 2. For any lambda strictly higher than 1 over square root of 2, this inequality is true. So this is like a proof of concept or an example. I don't know if you know other example of this. I would be interested if you have other examples of cases where you have a min-max problem, optimization, or a zero-sum problem, and you want to compute the saddle point, and you go to you introduce general sum games. You run some algorithm on the general sum game. You converge to the same stuff, but at a much faster speed. Let's illustrate this on a simple example. But I think here you have the main ingredients. So what is Wasserstein gain? It's an instance of GANs. The original GANs I've showed you before, it was related to the Jensen-Shannon divergence between the law you simulate and the true law. Okay, it's related to the Kullback-Leiber distance. This one is related to the Wasserstein distance of order 1 between two probabilities, so P and Q, which is the supremum of the whole Lipschitz function of the expectation of the Lipschitz function D with respect to the probability P minus the same with respect to the probability Q. And what do? We have, remember, we have the law of the true data, and we have the set of laws we can generate. We choose theta. Here, theta is theta G for the generator. So we choose theta, and we will generate one law in this set. So what is the distance from a point to a set? It's the minimum for all theta of the distance from the point to the element of the set. And this, because of the form of W1, can be written again as a min-max problem. It is very standard to do this. It happens in many cases. So this is a zero-sum game corresponding to Wasserstein game. Here you have no log. So let's look at one example. It's really a toy example, but it was used in previous papers, so we use the same. So assume the data, they follow some normal distribution, and what you don't know is a mean. Okay, N is very large, 1 million. Z, you have access to latent noise also normal, and M is much smaller, maybe 100. You don't have access to any generator, so this is only what you can generate. A1 is a fixed matrix. You choose theta, and you transform Z into the law of G theta of capital Z. Okay, so somehow you choose the mean here. And for the discriminators, you cannot choose any Lipschitz function, but you have a neural network. So here it's really a small set. It's a set of all functions d beta, which can be written like this. When A2 is a fixed matrix with spectral radius less than 1, so that all of these functions for every beta with norm less than 1, they are 1 Lipschitz. And if I write the W-GAN problem, I can write it like this. By definition, you do the computation, very easy. You end up in this formula, in this problem, which perfectly fit our framework. But it's a toy example. So here, y before is theta, x of before is beta, and we have some bilinear payoff function. A priori, what is different between what we had before? Here we have this constraint. Okay, but you can show that in this game, whether you put the constraint or not on beta doesn't change the value nor the optimal strategies of the generator. So you can forget the constraint and just consider this without the constraint. This is a set of Nash equilibria. So here we have some linear term. B is not 0. So this is why we have this expression for the Nash equilibria. For instance, if A is this matrix and V is this payoff, in the first case, we can consider the zero-sum game given like this. If you do theorem 1 and you optimize in eta, with the corollary optimizing in eta, you find this convergence rate. So this is the eta you need to fine-tune, you need to know it, and this is the convergence rate. So it's strictly less than 1, but it's close to 1. So it's fast, but not so fast. And if we do our technique, so you introduce this matrix. Of course, you have to think of much bigger matrices, which is just a toy example. And by the last theorem, so it will still converge to what we want to know. We want to find V, so we want to find 2V. And you can just always use 1/2 exactly for any matrix for the step side. It will converge, and the optimal rate will always be 1/√2, which is smaller than this one, and it's quite a good improvement. Okay, we can make pictures to see how faster it is. So here in blue, we have theorem 1 without optimizing eta, with taking the 1/2, the standard case. If we optimize in eta, you go a bit faster. But if you use the general sum game with what we recommend, somehow we have something which is much faster. So that was it. Let me conclude with my last slide. So what have we been doing here? So we have shown how introducing general sum games can speed up and optimally speed up to the optimal level of square root of 2 divided by 2, the convergence of unit problem. Okay, and I'm interested if you have other cases where general sum games help to solve zero-sum games. And this was in the unconstrained bilinear case, which is a very specific case. Okay, it is a very specific case. So what for GANs, for instance, what can be useful? So it says, okay, it's good to use optimistic gradient descent ascent for GANs, and not only gradient descent ascent, because we have certificate of convergence, right? Converge to a Nash equilibrium, which is also a certificate of stability of the solution. We have a saddle point. And if you can compute A plus, we can discuss this if you want, then we believe it's useful to go to the general sum game and using B is minus the transpose of A plus. What's more, many things more can be done. So first, of course, we can try to extend this approach to more general games. So there is some hope for convex concave game, and there are already some positive results in the strongly concave, strongly convex case. We can also, yes, say, but I want to study finite games played with mixed strategies, so bimatrix games. So then we need to project, each time we have an iteration, we need to project back on this simplex. Okay, so we know, or we think we know, we know that projected OGDA on the simplex converge to saddle point if you're in the zero-sum case. Okay. And if we are in the general sum case, bimetrics game with projection to the simplex, some variant of optimistic mirror descent converges either to Nash or in average to strong coarse correlated equilibrium. But in average, okay, maybe we cannot have better. But here what we have done is a last iterate convergence, which is much better for the stability. And towards applications, of course, what I've presented is a toy example. So in practice, there is some stochasticity in the payoffs. What you observe, you don't compute AY, you observe a sample of things with AY, you have mini batch. So it would be interesting to introduce stochasticity in the payoffs to go to something more realistic. And also, okay, dealing with really different function because there are some non-concave, non-convex properties of real instances of gains with a log and log of 1 minus that it's important to understand, and this is a challenge, but some things may be tried. Okay. For instance, we can also try to use to see when GDA converges. In the case where it converges, can the introduction of general sum games improve also the convergence? There are many questions we can start based on this work. That's it. Thank you very much.
Thank you, Jérôme. Are there any questions? And Jérôme, do you want to turn on your camera?
It's not on? Okay.
No.
What happened?
So, questions?
Yes. Can you hear me?
Yes.
So first question, two small questions. I hope. When you have Bx equal to the negative of the pseudo inverse, does this game have a unique Nash equilibrium? You know, like the one where you had 1, 0, 0, 2, and then you had -1, 0, 0, minus a half. This looks like a distorted matching pennies game. But so the question is it unique, the equilibrium of this non-zero sum game that you generate?
No, I think no. No. You can have, we can compute it exactly, but in general, you may have several. Even
with the special case of this inverse?
Yes.
Because
for instance, always, in these games, they are very particular on the bilinear game. The set of Nash equilibrium will always be a product.
Yes.
I know the component of player 1 because you only change the payoff for player 2. The command for player 2 because you only change the payoff for player 2 will be the kernel of A. So if A is singular, you will have many Nash equilibria.
Okay. And the second question
is, not a way to select equilibria. It's not a way to. We'll have exactly the same.
And the second one, you mentioned this bimetrics games. I mean, there is a paper by Mangasarian and Stone that minimizes a quadratic function. I'm not sure you know it. It's a very old paper that minimizes a quadratic function to find a Nash equilibrium. And it might be that if you use gradient descent for that quadratic function, I don't know, but I mean, it could be your version of yours. And I know that this minimization could get stuck in a local minimum. It's only when the minimum has value 0 that you have a Nash equilibrium. I mean, I'm not sure you're aware of that, but it would be interesting possibly to look at this comparison. The paper is Mangasarian Stone from in the 60s. I mean, really old. I can find it for you, but I don't know. Yeah.
Yes, I will be happy to have it. If you can write it in the chat or send me an email.
Yeah, I will.
I will be happy to look at it.
And it might be really, I mean, it would be good, and I can send you. It's not a big counterexample. It's already 3x3 games that fail to have this property, and so it would be interesting.
What would be nice, what would be our hope is maybe if you look at the zero-sum problem, it doesn't converge. Maybe if you modify the payoff function of player 2, then you will get convergence because it will be a special case and convergence to something interesting.
Yeah, I mean this is a general bimetrics game. That's what I'm saying. I mean, not related from a zero-sum game. It's coming from general bimetrics games. But okay.
But yeah.
Yep. Thanks. Sorry. Yep.
Thank you.
More questions? So Jérôme, I have a question, something simple. If I understood you correctly, X and Y's are in the Euclidean space.
Exactly.
What happens if we restrict them to the set of probability distributions?
Okay, so this was in my last slide. So probably it was not clear enough. There is a paper by Wei and other people in 2021. And I think they prove that the algorithm converges to saddle points.
Mm-hmm. Okay. Thanks.
It's more difficult if it's non-zero sum. But in the zero sum game, if I understood correctly what they do, they prove this.
Okay.
Because yeah, it's a good question. In practice, you know, they fine-tune the parameters, so the theta G and theta D. So these are there are finitely many parameters, but it's huge. So the question is it compact or not? What they can generate? And I think they don't put capacities. They try everything, and they think if the window is large enough, they will find the saddle point. But still, I think for us, it's very interesting to look at this case of fraction in the simplex.
Yeah. Thank you. So if there are no more questions, we'll thank you, Jérôme, for the presentation, and we will meet again in 2 weeks.
Thank you very much.
Thank you.